Hi there. All right. Welcome to today's lecture on matter, the states of matter and kinetic energy. Today we're going to learn about just some of the stuff that's going to be reviewed from, back when you were younger in fourth grade or whatever. But now we're going to talk a little bit more about the energy of the molecules. As we begin to explore chemistry and physics at the upper levels, we want to start thinking about things in terms of the motion of the particles, and we think about what's called the kinetic molecular theory. So today we're going to be kind of diving into that a little bit, talking about the states of matter, but let's make sure that we're focusing in on what's happening to those actual particles as we talk about that. Now, that's such an important thing to do, because when we can start looking at the world in terms of a molecular point of view, that's chemistry, right? Looking down and diving down into the deeper parts of the chemicals, the finer points of the chemicals, then you start understanding the world in a much better way. It's not just superficial, like, yeah, that kind of works, but now you know what's happening behind the scenes, why it's actually working the way it's working. So it's really fascinating. So this is chapter 3. We're going to start with section 3.1, matter and energy. Okay, our objectives today to look at the kinetic theory and use it to describe the structure and properties of different states of matter, solid, liquid, and gas, and we're going to touch on plasma as well, and then to distinguish between temperature and heat. Okay, those two things are different from each other, and we want to talk about those as well. All right, so the kinetic theory. Atoms are tiny particles that are always in motion. The higher the temperature, the faster the particles move. And at the same temperature, more massive particles move slower than less massive ones. Okay, so 3 basic components of the kinetic theory that we want to go through here today. And the biggest one that we start with is all matter's in constant continuous motion. All right, even solid things like this, your desk or the table that you're sitting at right now, those things, although they're solid, they are having little particle parties inside. Okay, all those little particles are shaking around and shimmering around. Now, they stay in a fixed position for the most part, but they're vibrating. Okay, all particles are in constant vibration. Solid particles are just vibrating, and then we go into liquid and gas particles are moving even more. Okay, so the higher the temperature, the faster the particles move. If I can start increasing their kinetic energy, I start increasing the speed of those particles, then those particles are now exhibiting higher kinetic energy. And the result of that is that we now have a higher temperature object. So a liquid is going to have a higher temperature than a solid because the liquid's particles have a greater energy. They're moving more, they're moving faster. And then a gas's particles are moving even faster than that. So a gas is actually going to have even a higher temperature than the liquid did at that same substance, okay? Excuse me. So at the same temperature, more massive particles are moving slower than the less massive particles. So think of atoms. And if you have actually, let's think of a bowling ball. If I think of a bowling ball versus a tennis ball, and I take a bat, whack, and I whack that bowling ball, is it going to move as fast if I whack the tennis ball, whack, with the exact same amount of force? No. The tennis ball is going to move a lot faster than the bowling ball, okay? Same thing with atoms. If I have a big atom, a more massive particle, it's going to move slower than the less massive ones. Okay, given the same amount of energy. Now, kinetic energy, we're going to learn a little bit more about that in the physics portion of our class next semester. But basically, the idea is that the more massive something is, the more energy it has at a given speed. Okay, so let's look at these 3 and see if we can figure these things out. All right, particles in your desk, are they moving? Yeah. Particles in your desk are always in constant motion. Now, we can get to a temperature at which the particles in your desk stop moving, and that's called absolute zero. Okay, so that is the point at which all particles cease their motion. When are water molecules moving fastest? At 25 degrees Celsius or 40 degrees Celsius, right? Well, particles are moving fastest at 40 degrees Celsius. They have got more energy, right? Just like you, if you were kind of a little bit sluggish, you wake up in the morning, you're kind of like, whoa, yeah, okay, getting out of here. And then by the time you get to the middle of the day, you're like, lunchtime, lunch, right? You're going crazy. You're ready to go to lunch. Well, that's kind of the idea, right? You're moving fastest at a higher temperature. That doesn't really translate, but it was kind of fun to go crazy and scream around, right? So anyway, 40 degrees Celsius, faster particles than 25 degrees Celsius. For instance, smell is going to travel faster in warm air than in cold air, okay? All right, relative mass of helium, neon, and argon is 1 to 5 to 10. Which one is going to move the slowest? Well, the biggest one is going to move the slowest, so that answer would be argon. Okay, so let's look at an example of these three states of matter, and they're molecules, right? They're particles. Let's think about particle motion. So if we were thinking about a liquid and a solid and a gas, the solid is in fixed position, okay? Notice that the ordered arrangement, think of an ice cube, crystalline shape. The liquid is not quite as designed, is it? So it's not as orderly. Now these guys are moving around each other, okay? The solid's fixed, but the liquids are moving around each other now, okay? And then if we go to a gas, the particles of the gas are moving so fast that they break the bonds of attraction they had between them, and now zipping all over the place. You can try to show that if you're drawing a particle model, show it with some extra lines that are zipping around, right? Okay, so now I want you to create a table, and you'll just do this in your notes section, and you're going to create a table of the three states of matter, solid, liquid, and gas. There are more than three states, but that's the ones we're going to talk about now. And then we want to make sure that you have some examples of each type of matter. I'll show you an example of that table here in a second. But let's talk about the movement and the closeness of the particles. In our table, let's talk about the shape, whether it's definite or variable. And let's talk about the volume, whether it's definite or variable. So create a table with that. Let's talk about it as you make it, okay? So let's talk about what we want to include. In the solids, what do we want to include? We want to make sure that we're talking about those particles being close and in fixed position, okay? Vibrating, show them vibrating. A little line on the side, vibrating would be good, okay? So what's the shape? Volume, what's the shape and volume of these things? Definite shape, definite volume, okay? Solids have definite shape and definite volume. They're not going to change. All right, the liquids. Now, I will say that if you have super strong, powerful presses, that you can make solids compress just a little bit. But you can do that same thing with liquids. Yet we don't really talk about it that way. We talk about them as being definite. So liquids, the particles are close, but they're sliding past each other. Now, I will tell you that water is an example of an exemption, an exception from this rule where solids have a closer contact than liquids. So in water, the solid is actually further apart. The particles are further apart. And that's why water's ice is less dense than liquid water. But that is very unique in the world of material sciences, okay? Not many things do that. So in general, solids have closer particles than liquids. But in water, it's actually the opposite. All right, so shapes. Liquid shape, that can change, right? So an indefinite shape, a variable shape. And its volume, that one is fixed, okay? Again, these things can be very slightly compressed, but we're not talking about that right now. That's not going under our standard issue information, okay? Gases, particles are far apart. So far apart, they don't have any attraction to each other anymore, okay? They're way far apart. They move independently. They're not moving together. And gases are mostly empty space. Take a good deep breath of that mostly empty space. Okay, well, I mean, again, yeah, I mean, there's plenty of air out there, right? And we need that air. But compared to a solid and a liquid, these things are really spread out, okay? And the shape, indefinite shape, indefinite volume, they're variable for both, right? I can take a gas and I can change its shape in the balloon, blow up the balloon, you can change the shape, and you can change the volume. You can compress a gas, you can expand that same amount of gas and let it fill up a different size container. So now, you've made a table. What does it look like? Maybe it looks like this. Okay, solid, definite shape, definite volume, close particles, vibrate in position due to strong attraction between the particles. An example might be ice. A liquid, variable shape, definite volume, close particles slide past each other. Liquid water. A gas, variable shape, variable volume, particles are far apart and move fast. Did you know that some of these gas particles that are striking your face right now are traveling over 1,000 miles an hour? I read something in Quora. I don't know if you guys know what Quora is, but it's a pretty interesting website where people get to kind of contribute their knowledge. Guy asked the questions like, what would happen if a single atom of iron struck me at 28,000. I can't remember if it's meters per second or miles per hour. But basically, you look at the amount of kinetic energy, nothing. Okay, these things are so many particles of air that are striking you right now, and they're going so fast. Many of them are over 1,000 miles an hour as they strike you right now, and you don't even notice it. You've also got those same particles inside your body, also traveling about the same speed, right? And so you've got a little balance of pressure there. So it's kind of cool. Anyway, gas, water vapor. Okay, so composition of ice, liquid water, and water vapor. They're all water, okay, but they have different compositions. So in states of matter changes, right? When a state changes, that's okay, but the actual composition of the substance doesn't. The energy changes. The amount of energy that's present in solid water is not as high as the amount of energy present in liquid water, and the amount of present in the same mass of gaseous water is going to be much higher than the amount of energy in liquid water. So the energy can change, but the substance does not change. Okay, let's see if you can pause it and solve this problem. Okay, list an order of decreasing strength of molecular forces: oxygen gas, Plato, rubbing alcohol, molasses, and granite. So what are you trying to do as you're solving this? You're trying to figure out which ones are more solid, right? Which ones have greater attraction? Which ones have greater speed of energy, right? So which ones are liquid, solid, and gas? So decreasing strength of molecular forces. The strongest molecular forces are going to be those solids. So I better have a solid first, right? So I better have something like granite first. And then as I go, I'm going to start making it go from that to a liquid to a gas. Molasses and Plato, which one is going to be most fluid? Plato might be a little fluid over time. Actually, kind of just solidifies and gets solid sometimes. But yeah, so Plato is probably going to be next, right? You can still move it, so it's obviously not as tough as granite. It doesn't have quite as strong of attraction as granite, but it doesn't flow in the same way, right? And so Plato is going to be the next decreasing strength, and then molasses, right? Really thick and viscous. And then we go to running alcohol, and then oxygen gas, right? That should be your order that you had there. Boom, 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 right? All right. So let's go on to our next one. Let's talk about a fluid. Because a lot of times when we think of the word fluid, we think of the word liquid. Fluid is not the same thing as liquid. A liquid is a type of fluid, but gas is also a type of fluid, okay? It's just a state of matter where those molecules are free to move past each other. And so a solid is not a fluid, but gases and liquids are. So if you can think of something that will pour, you're thinking of something that is a fluid. Now it's actually kind of cool because there's like this webcam in this lab in New Zealand where they've got the thickest fluid known to man, and they keep this camera on it all the time. People watch it just for fun, but it has like one drop every like 12 years or something. And then like 12 years later, it finally drops again. It's like tar, basically. Super thick tar. It's kind of cool though. It's still a fluid, still flowing, just really slowly. Okay, and then plasma. Now we want to talk a little bit about plasma. Plasma is a really cool state of matter, and I got to tell you, when I was in school, plasma wasn't a thing. At least they never taught us about plasma. Okay, all they taught us is solid, liquid, and gas. And they told us that stars were made up of gas. Well, now we teach that stars are made up of plasma. And so whereas when I was in school, they taught me that gas was the most common state of matter, today I'm teaching you that plasma is the most common state of matter. And what's crazy is that scientists are disputing how many states of matter we really should be teaching. Who knows how many states of matter your kids are going to get taught? Because there are like, some scientists say that there are like 16 different states of matter that we could be teaching, including Jello. Like, is it a solid? Is it a liquid? Maybe it's its own state of matter. One of them was the Bose-Einstein condensate, which was actually discovered at the University of Colorado in Boulder. That's one that a lot of people are saying. I think it's probably going to be the one that they are most commonly going to say is another state of matter once they get down to it. And even information. What? I just read an article that talked about how information might someday be considered a state of matter. Because when you think about all of the information that's being converted, right? And you have all this information that is now turning into the ones and zeros in computer systems, that the amount of the earth that will have been converted like physical Earth that will have been converted into information within the next like 300 years is, I don't know, it was a stupid number. I didn't even believe it, but it was like gazillions of tons or something. I don't know. Gazillion, that's a real word. No, it's not. All right. So anyway, lightning, the fluorescent bulbs that we have in our ceilings, these things have plasma in them. Plasma TVs, of course, right? The way that your fluorescent bulbs work, plasma is basically a gas that's been super excited, right? And so in your fluorescent bulb, you have mercury vapor, mercury gas. And when you energize it with the electricity, that excites the mercury vapor and it starts to knock its little electrons getting knocked off, and so you end up having these charged particles. So a gas and a plasma are very similar, but plasmas are good conductors of electricity because their electrons have been knocked off because they're moving so fast, got so energized, and so those little mercury vapor pieces, which are now plasma, now shoot their little electrons and they hit the fluorescent coating, the phosphorescent coating, fluorescent coating that's on the fluorescent bulbs, and that emits this light. Isn't that cool? As soon as you turn it off, mercury turns back into a gas. Should not do Star Wars stuff with those fluorescent bulbs because it actually emits a mercury gas. Mercury is toxic to you. Don't sniff that stuff. All right, and what else? Yeah, so similar to gas in variable shape, most common state of matter, cool stuff, right? Plasma balls. You guys have seen those little plasma balls that you touch. Got one right over there. You can come in and check it out in my room. That's also plasma. All right. So now we've talked about the states of matter. We've talked about energy. Let's just kind of dive into a little bit more about energy in terms of what actually it is. And then we're going to talk about temperature and heat. I think it's the next lecture, actually. So energy, the ability to change or move matter or to do work. So if I want to get work done, it's going to require energy. Think about that. Like, how am I going to move this from here to here without energy? I've got to have energy, right? I've got to move it. So energy is the ability to do work. Makes sense, right? There's different types of work, energy that we can talk about, kinetic, potential, different types of energy conversions. But let's talk about kinetic energy. This is energy due to motion. So we'll talk about potential energy at another time. But kinetic energy is the energy of motion. So if something is moving, that's kinetic energy, okay? Energy due to motion. Now let's talk about these in terms of kinetic energy now, right? Which one has a greater kinetic energy? Does the solid, the liquid, or the gas have greater kinetic energy? Which one is moving more? The gas. That has greater kinetic energy. Now I want to tell you something real quick, kind of cool. They're showing you the steam over there, right? The part of that little, tea kettle where it's all cloudy, it's actually not a gas. This part up here is a liquid. The part right here, which is actually invisible, if you've ever looked at a tea kettle and you look really closely, it's clear up until a certain point, and then it starts turning into the smoke. Well, that smoke is actually not smoke, right? It's water vapor. It's actually condensed back into a liquid again. So it's like a cloud up in the sky. Those are made out of liquid. The part that's a gas, which is actually really hot and really dangerous, and don't touch it, is the clear stuff. The stuff right before it turns into the cloud. That is the gas and has a lot more energy than this cloud. It's not so bad to put your hand kind of on there, at least for a second, on this part right here. But you put your hand down there, it's going to hurt, okay? That's hot stuff, and it's going to basically just transfer a ton of energy into your hand right at once. All right, so temperature versus heat, all right? Temperature is not the same thing as heat. Temperature is the average kinetic energy of a substance. Heat is what we usually refer to as a transfer of energy from one object to another, an object that has higher temperature to an object that has lower temperature, all right? So temperature, average kinetic energy of the particles in an object. Remember that temperature depends on the speed of the particles, but not the number of particles. So I could have this pool that's at a particular temperature. I put the pool at 70 degrees, and I could have a little cup or a little syringe of water that's 70 degrees. They can have the same temperature. So it depends on the speed of the particles. Temperature is average kinetic energy of particles, but it does not depend on the number of particles. However, if you look at heat, that's the total amount of thermal energy that we have in something, or the transfer of energy, okay? Sometimes people like to define that a little bit differently, like Thermal energy is not the same thing as heat sometimes in some texts, where heat is referred to as a transferring of that energy. Okay, here in our text, it's a little different than in your chemistry text that you'll use in a couple of years. But thermal energy is the total amount of energy. Heat is the transfer of that energy from objects that are warmer to colder. So, in this case, different texts are a little bit different. Here, they're not wanting you to get too complex, but I always like to make it as complex as it really is because you're smart enough to figure it out. But anyway, thermal energy, total kinetic energy of the particles in an object. Okay, the thermal energy does depend, on the speed of the particles and the number of the particles. So if I had a pool that had a ton of particles on it compared to a little syringe, they're both at 70 degrees Celsius. The pool has a lot more thermal energy than that little syringe. Okay, think of it this way. If I had a pool of boiling water and I had a syringe of boiling water, which would you prefer to have dumped on you? Okay. Well, the syringe, right? Well, because instinctively that pool has a lot more thermal energy than that little syringe. No duh, right? That's pretty obvious. So thermal energy is the total amount of energy, both the speed of the particles and the number of particles are calculated to get a total kinetic energy or total thermal energy. And heat would then be, and again, we'll get into that more, you'll talk about it more in chemistry this way, but it's that transfer, right? So how much heat can transfer? A lot more heat can transfer from the pool than can from that little syringe. Okay? All right. So let's ask a question. What if water is poured from a teapot into a mug, which has the higher temperature? Water is poured from a teapot into a mug. Immediate measurement, they should have the same temperature, right? Mug might have cooled down a little bit. It was exposed to the air and all that kind of stuff, but same temperature because the speed of the particles is the same. Okay, the teapot has more than the mug, but the particles are moving the exact same speed, right? Which has more thermal energy? Well, the teapot has more thermal energy, right? Because it's got more particles. Compare a lit match to a jacuzzi, which has a higher temperature. Oh, let's see, burn myself on a match or burn myself on a jacuzzi. No, the match is going to have a higher temperature, right? That's going to be dangerous. It's got faster particles. The particles in that gas are really moving fast, okay? And so, which has more thermal energy? Well, a jacuzzi has got a lot of particles. So even though that match is what's going to burn you, the jacuzzi is going to have more thermal energy because it's got a lot more particles, okay? So it's about the particles and the speed of the particles, the number of particles and the speed when you're talking about the total amount of thermal energy. Okay, fun. Let's review our objectives. Can we now use our kinetic theory to describe the structure and properties of the different states of matter? And we can even talk about plasma, right? Talk a little bit about that one. We know about solid, liquids, gas. We made a little table out of it. And can we distinguish between temperature and heat? Sure can. They are not the same thing. And again, we like to say thermal energy there. Heat is a thing, and it's all about transferring energy. But again, in some texts, they're not gonna like you equating heat with thermal energy. In this one, it's a little different. It's okay. Different texts can be a little bit different. You're gonna learn about that as the days go on. It's a little frustrating, but it's okay. All right, well, fun time today. We learned about some really important concepts, and it was great having you here. Why is it important? Man, this stuff is available and important every single day. We see that we get to use this stuff, right? The temperature of the weather outside, the temperature of the room. How do I stay warm? These things are going to have to do with, how those particles are moving. What's the difference between a solid, liquid, and gas? Which one has more energy? All this stuff is day-to-day kind of stuff that we can incorporate into our lives. And so as we go through the year, we're going to be talking about all these things. This is kind of foundational. We build on so much of this. And the biggest part of this lecture, remember, is kinetic molecular theory. That all particles are in constant motion, even things that are solid. All right. Hey, it's great having you here today. You're here somewhere, I think, behind that light, maybe. I don't know. It's a little bright. God bless you. Have a good one.